Welcome to clickmyproject.com. A spectrum switching delay over scheduling algorithm for centralized cognitive radio networks. When a cognitive radio device changes its operation frequency, it experiences a hardware switching delay to tune to its new frequency before it can fully utilize it. This delay in general depends on the wideness between the two frequency bands. When the range of frequencies that the cognitive radio network operates in is narrow, this delay difference might be negligible, but the cognitive radio networks of the future are envisioned to operate in a wide range of frequency bands. So the spectrum allocation and scheduling algorithm designed for the cognitive radio networks have to take into account different delays that occur while switching to different frequency bands. The dependence of the switching delay on the wideness between the old and the new central frequencies is unique to the dynamic spectrum access paradigm, since other wireless technologies typically operate in a narrower bandwidth. Cognitive radio networking achieves high utilization of the scarce spectrum resources without causing any performance degradation to the licensed user. During the switching of the cognitive radio networks to different frequency bands, the user experiences a hardware delay. The proposed system addresses this hardware delay problem as a scheduling problem. The proposed system uses a polynomial time suboptimal algorithm to address the scheduling algorithm. The polynomial time suboptimal algorithm is a S2DSA, that is spectrum switching delay over scheduling algorithm. This is the flow of our project. Consists of 5 modules: network formation, channel allocation, spectrum sensing, S2DSA algorithm, and performance evaluation. In network formation, we create the system architecture, that is primary user. Primary user has a license to operate in a certain spectrum band. This access can be only controlled by its base station and should not be affected by the operations of any other unauthorized user. Primary base station. Primary base station is a fixed infrastructure network component which has a spectrum license. In principle, primary base station does not have any cognitive radio capability for sharing spectrum with cognitive radio users. However, primary base station may be required to have both legacy and cognitive radio protocols for the primary network access of the cognitive radio user. Cognitive radio user has no spectrum license, hence the spectrum access is allowed only in an opportunistic manner. Capabilities of the cognitive radio user include spectrum sensing, spectrum decision, spectrum handoff, and cognitive radio MAC routing transport protocols. The cognitive radio user is assumed to have the capabilities to communicate with not only the base station but also other cognitive radio users. Cognitive radio base station. Cognitive radio base station is a fixed infrastructure component with cognitive radio capabilities. Cognitive radio base station provides single hop connection to cognitive radio users without spectrum access license. The second block is channel allocation. There are two types of channel allocation schemes: are distributed channel allocation scheme and centralized channel allocation scheme. In distributed channel allocation scheme, based on the 3 parameters: co-channel distance, signal strength measurement, signal to noise interference ratio. For our process, we can only use a distributed dynamic channel allocation. DCA is a distributed channel assignment scheme for cognitive radio networks, which assigns channels based on the minimum interference to primary user nodes, maximum connectivity, and minimum interference between cognitive radio users reuse. Every cognitive radio node checks for primary user activity and calculates the channel quality for all the available ideal channels based on the maximum connectivity and minimum interference within cognitive radio nodes. The best channels are assigned for those which give greater value for channel quality. After calculating the best channels, cognitive radio node assigns the best channels to its first interface and second best to its second interface. The third subblock is spectrum sensing. It is the process of searching the ideal time slot which is not allocated to the primary user at the particular time. Spectrum sensing process is done by using the non-stationary hidden Markov model. Non-stationary hidden Markov model is a dynamic Bayesian network which is the action can takes place through the previous observation. The next subblock is S2DSA, that is spectrum switching delay over scheduling algorithm. Before the ideal channel is predicted by using the non-stationary hidden Markov model, the ideal channel which is ideal is sent to the S2DSA algorithm, a novel algorithm that solves efficiently the problem of spectrum sharing and user scheduling in a cognitive downlink MIMO system. We design a S2DSA algorithm which includes the spectrum switching delay to maximize the throughput. Maximum possible packet delivery is often every user can be calculated, and then they are allocated to the particular time slots. After allocating the users into the time slots, and then we can calculate the performance evaluation. Computer simulation so that our proposed algorithm is able to achieve near optimal performance with lower computational complexity. We also compare our proposed method with the corresponding constant switching delay based algorithm and demonstrate that our suggestion of taking into account of different hardware delays while switching to different frequency bands is essential for scheduling in cognitive radio networks. Open the source code folder, run main.m file. New guide window will appear, and initially we form the network. This is the cognitive base station, and the remaining are the primary base station. Calculate the resource by selecting number of channels. Calculate resource, the number of resources 40, and then node deployment. Deploy the nodes for each and every base stations. After calculating the node deployment, and next is spectrum switching delay our algorithm. It asks for enter the primary user, allocate the channel to first set of primary user. If yes means press Y, or else press N, no. The ideal before secondary user allocation is second channel, third channel. Now is ask for another question for secondary user. This is power spectral density. This is the peak represents the allocated user, and the low for non-allocating. These are the throughput values for each and every user. I consider 20 user of secondary user. This is the started throughput, and this is a non-significant Markov model output. And I've got the delay difference for existing and our proposed algorithms. This is the switching delay by throughput versus this is our proposed algorithm. Green color is our proposed algorithm. Compared to existing method, our proposed algorithm achieves highest throughput of 3800, nearest 3800. After that, number of channels used, frequency versus throughput. Compared to existing method, our proposed algorithm throughput increases. Then number of secondary users versus throughput. Compared to existing method, our proposed algorithm achieves high throughput, and it is for variable frequency versus throughput. The number of secondary users is total average throughput. This is for frequency 20 and 20 for our proposed algorithm. From this, I conclude that our proposed algorithm achieves highest throughput and lowest switching delay than the existing method in the literature. Thank you.